So once again, a very good afternoon to all of you. We were talking about loudspeakers, and last class we took long back, and after that I took some break. I had some personal work, and then this week one holiday and one discussion lecture. So we are back to the lecture taking after a fairly long period of time. We were talking about baffles and enclosure. Today we were talking about loudspeakers. In that we spoke basics of a dynamic loudspeaker. Today we are going to talk about baffles and enclosure, air suspension, low frequency loudspeakers, equivalent circuits, and vented box or bass reflex, whichever way you pronounce it. So let's look at what do we mean by baffles and enclosures. Now if you have a speaker over here, then the speaker vibrates, the diaphragm or the cone of the speaker vibrates back and forth. As the diaphragm or the cone of the speaker vibrates back and forth, what happens is, look at it carefully. As it moves forward, it creates a high pressure zone in front and a low pressure zone behind. As it moves backward, it creates a low pressure zone behind and a high pressure zone forward. So you can now see that there is a wave going in the forward direction, and there is a wave which is also going in the reverse direction. So basically a loudspeaker emits two waves which are phase inverted in two directions. One is in the forward direction and one is in the backward direction. Okay, there was some noise at my end. I just closed my window. So, yeah, so you can see that the speaker gives two waves, one in the forward direction, one in the backward direction, and you will find that these are phase inverted waves. Okay, so what happens is typically this wave will spread in all directions, this will also spread in all directions, and since they are phase inverted, they tend to cancel out each other. As a result, the overall sound output decreases. In order to stop this, all we do is we provide a shield. So you provide a shield over here in both the directions, in all directions. Typically you take a sheet in which you make a circle and you put the speaker. So this shield acts like a baffle or a divider. It is typically technologically called as a baffle. It provides a shield from short circuiting the waves. Okay. So radiation drops. Now it has been experimentally observed that at lambda by 4, the radiation drops, in a sense that if the size up to a distance of lambda by 4, the sound output decreases drastically, and therefore baffles at least has to be larger than lambda by 4 in length. That is, this length has to be greater than largest lambda, or the smallest frequency that the speaker is producing. Calculate lambda for that, and it should be larger than lambda by 4. Okay, the tuning fork and speakers are heard louder with the presence of the baffle. These are simple experiments. You have a tuning fork here, you just bang it and hear it. You will find the sound is very little. Typically when you do that in your lab or wherever, you find that it's very difficult to hear them. Now you put them in cut a cardboard this way and put the tuning fork in this, so that the cardboard acts like a baffle and your frequency is blocked. You can hear more sound, more stronger sound in this case. Similarly, if you have a speaker placed in air, small speaker, it will not sound that loud, but make a hole in a cardboard and put it there, it will sound much louder. So these are the examples which shows that a baffle can make sound much louder than what it is otherwise. Now, an ideal baffle could be an infinite baffle where the baffle extends everywhere. So when the baffle extends everywhere, then there's a complete shielding of the back wave and the front wave. And in that case, a decent amount of sound is heard. The only drawback is that getting an infinite baffle is really challenging. And although we can make it, we can mimic it mechanically, I will talk about it in a while. And second is the the back wave is wasted in the sense that you are having a back wave of sound that gets wasted in case of infinite baffle. And therefore there are a number of other designs which are used in speaker design and which is the subject matter of today's class. And these are called bass or bass reflex, drone cone, rear horn, etc. So one of the simplest modification in design is that you put an air suspension. Remember, infinite baffle is next to impossible, a real infinite baffle. For example, you cannot make a complete wall with a hole at the middle dedicated to put a speaker. You can't do that. It has to be kept in a box. Now, if the box is large, much large compared to the speaker, in that case, the air absorbs all the back wave almost. Whatever back wave goes in the, if it's a large volume of air, then almost all the back wave is absorbed. In this case, the air compliance is much greater than the compliance of the suspension. You know what is the compliance? Compliance is reciprocal of stiffness. We spoke about it in the last class. It's a reciprocal of the stiffness. So if it's a large air volume, then air is tend to become very soft. In compliance is much higher, and therefore the most of the back wave is absorbed completely, and that design is equivalent to infinite baffle. Remember, this is when the box is much larger than the speaker. However, if the box is not much larger than the speaker, as it is shown in this diagram, now in this diagram you can see that the speaker is fairly large compared to the size of the box. So in this case, this air trapped over here hits back. Typically, you can understand what is happening. When the speaker hits it behind, the air mass hits the enclosure behind, and the enclosure applies a reactive or a reaction force which makes the air to move forward and hit back to the cone. So if this mass is less, then it acts like a hard spring, or the compliance, which is a reciprocal of the hardness, becomes less. So if this box is large, back wave does not hit back. If this box is small, the back wave hits. So air provides more restoring force than the suspension, and this this complete thing will be hit forward. One example where you can experience this force of air is in your home. If you keep windows more or less closed, and if you shut or open the door quickly, so if you shut or open the doors quickly, you will find that the window pane vibrates or they shake back and forth. That indicates the fact that opening the door on one side pushes on the other side. So that is a rough example. However, a complete, that here it's a vibration, and it's a vibrations going on, and we are talking about a wave here. So remember, again, I'm telling you the key points. Very large box will cushion out all the back wave and it will be negligible. Compliance is much greater, and it is equivalent to infinite baffle because all the back wave is lost. That's how you practically realize an infinite baffle. If the box is small, in this case the back wave hits harder back on the cone of the speaker, and it provides more restoring force than suspension. This design was patented by Harry Olson, stalwart in the audio engineering, microphone and speaker designs. In fact, he started a company called RCA, which is still working. They produce one of the best microphones in the industry. This kind of design is low efficiency. It says low on efficiency, but it is space saving, and even smaller speakers can produce low frequency. Remember, we were talking earlier that for small speakers, producing low frequency is very challenging. So here that can be done. Equivalent circuit of a speaker. Typically, an equivalent circuit of a speaker is can be drawn in terms of LCR series. Uh, the compliance or the softness of the spring air system can be represented by a suitable capacitor value. Mass can be uh, indicated by a suitable inductor value. Mass here means the mass of the diaphragm and the mass of the air which is moved vibrating. And third is the damping, which can be realized using resistor. You can drive it by an AC signal, which is equivalent to a signal that drives the speaker. And once you run your algorithm, your calculation, you are all well familiar with LCR series circuit. They give a resonance curve at a particular frequency, and the particular Q value can be calculated. So this is typically this circuit which is used to practically uh, or theoretically simulate the real speakers. Q is equal to 1 is called critical damping. Q greater than 1 is called maximum flat response. Different kind of Q values could be needed for different kind of music. So for piano, Q is 1, and for pop music, Q is greater than 1. You can see here is the typical response. Q is 1 is almost a flat response. This is 1, so almost flat and then drops. Q greater than 1 means it shoots up slightly up and then falls. So the lower frequencies are amplified. This is, by the way, resonant frequency. Here's frequency upon resonant frequency. So you're comparing the frequency with the resonant frequency. So if you're at resonant frequency, if you have a high Q, then the output increases in dB. So here comes the next modification. First was a simple box, but now we talk about a vented box. Now what happens in a vented box is small port is created in the front here. This is the small port. So this is my box, this is my speaker. The front wave will go this way, back wave will go this way. But now what we do is we produce a small leakage here, a small port. So now what happens is this, look at this box carefully. You are driving with one wave here and you are allowing the sound to go out from here. This is very typical to a Helmholtz resonator. Some few of you are doing some experimental work on that as well. Helmholtz resonator. So you are familiar with that idea. You drive it at one end and let the energy escape on the other end. So at the frequency, the important point that we have to remember, this is the mechanical analog. Like this is the speaker. So the speaker is represented by a piston which is vibrating back and forth, and the mass of the air inside is vibrating here. Now remember, at the frequencies below resonance, the mass of air moves in phase with the driver. You have to remember this fact. And the radiated sound will be out of phase with respect to that from the speaker. So basically you have to remember the second point. The radiated sound will be out of phase with respect to the speaker. So at low frequency, the sound output will become out of phase. So like if this pushes inside, something happens here, and then a compression is created, a rarefaction is emitted, something like that. That is at a low frequency, frequency below resonance. Frequency above resonance, the reverse happens. That means your radiated sound will be in phase with respect to that from the speaker. So the radiated sound gets in phase, means whatever sound is coming out, if a compression is coming out from here, a compression will come out from here too, but at a high frequency higher than resonance. Frequency radiated from the port exceeds at the cone. So whenever the resonance happens, that means the speaker is vibrating at the same frequency as the resonant frequency of the Helmholtz resonator. And in that case, the amplitude of the sound coming out from the cone becomes much louder than the amplitude of the sound coming out from the speaker. That's the point. That the sound radiated from the port exceeds from the that's radiated from the speaker, but at a resonance. Remember that. So you can now see what we are basically doing is we are using the back wave. We are giving a path to the back wave to get emitted in the front and somehow correlating with the speaker and balancing the two to produce a larger output. Here is another graph. This is the resonant frequency F0. Now, if you have an infinite baffle, which is the solid line, at resonant frequency slightly above the resonant frequency, you get a high output, and then the output drops linearly. When it is closed box, then at a frequency, if you are at a frequency below or lesser than or much lesser than the resonant, it is out of phase and the output drops sharply. As you go close to the resonance, the phase difference reduces and the output increases. At resonance, the output remains high because the the vent gives much stronger sound, and above resonance it starts coming in phase, the sound output relatively remain high, although it drops a bit because the resonance situation is dropped, but this is how typically you will get the output here. So out of phase sound results in cancellation in the A region. In B region, the sound output by port is way higher near resonance. So B region, and in phase enhances the radiation in the C region. D region, again it remains in phase, so it remains high, but the resonance situation is lost, so there is a slight drop. So a vented box bass reflex enclosure has many advantages. Cone has to move smaller distances. So because of that, it can handle higher powers and lower distortion. Remember, when I come to distortion, perhaps in the next class, I will talk about that larger cone excursions lead to larger distortions. Lower cutoff frequency by the same driver. So we have seen in the previous graph that if it's a vented enclosure, then the low frequency output improves and you get lower cutoff frequencies. High efficiency by the same enclosure. Same enclosure gives you higher power handling and higher efficiency as well. Here is an experiment again to find out the impedance curve. You have an audio generator. In the lab, we can do these kind of things. You have a resistance, voltmeter, speaker. So you figure out, you change the frequencies, find out the current, find out the voltage across the speaker. Impedance increases. If it's an open speaker, impedance increases at one frequency, no baffle. at one frequency, drops and then increases. If it's a baffled speaker, like if you put a baffle here and here, then this peak drops drastically and then again it goes on increasing. So we do these kind of things in the laboratory. I doubt if it is possible without lab. Drone cones are interesting. Instead of using a vent, we use a dummy speaker over here, just a speaker cone without any circuit. So what happens is the back wave, which is, this is a real speaker, it produces back wave, front wave, back wave, everything. But the back wave hits this speaker and this speaker starts vibrating and then produces sound output. Sometimes it is also kept large so that it can produce very good low frequencies. So that's a drone cone speakers, we call it. These are the horn speakers. So you can have a long tube here and then the sound comes out. They are typically called as horn speakers. Tube can be very long. This is one-sided horn speaker. This is a double-sided, one on this side and one on this side. So instead of just creating a vent, you first create a tube. The length of the tube creates a resonance mechanism. It undergoes a resonance tube and that enhances the sound quality or sound output. The length of the tube varies from designer to designer or companies to company or from speaker to speaker. There is something called as acoustic labyrinth where the backside wave is adjusted or delayed by an amount lambda by 2 so that when it comes out it comes in phase with the speaker, again further enhancing the sound output. So there are various possible designs, various possible ways to do it. As you can see, this is why we call loudspeaker designing as a dark science. For example, there is no standard fixed way to design a loudspeaker. Materials vary, the designs vary, and therefore if you have to ever invest in a good loudspeaker, you must listen to it carefully many times. If you like the sound, then only you should buy. You should never buy a loudspeaker just on the basis of the description. So yeah, we can stop in this lecture over here. Thank you.